Hello everyone, I am Jebastin, Assistant Professor in EC Department, PSN College of Engineering and Technology. We are going to discuss about sampling. Sampling is the most important in communication. In nature, generally the signals are analog form. For example, speech signal, weather signal, temperature signal, ECG signal. So these signals are in the form of analog form. So we must convert the analog form into digital form. So we go for sampling. To process the analog signal by digital means, it is essential to convert them to discrete time signal and then convert them to a sequence of numbers. The process of converting an analog to digital signal is called analog to digital conversion. Types of signals. First one, analog signals. Analog signals is nothing but it is continuous in time and amplitude. For example, voltage, current, temperature, these are the analog signals examples. Next one, digital signal. Digital signal is discrete both in time and amplitude. Example, pulse waveform, on-off switching. These are the examples of digital signals. Next one, discrete time signals. Discrete time signals is discrete in time and continuous in amplitude. Already I told, analog to digital conversion involves three steps, which are sampling, quantization, and encoding techniques. First of all, we define the sampling theorem. Sampling theorem states that continuous form of a time variant signal can be represented in the discrete form of a signal with the help of samples, and the sampled or discrete signal can be recovered to the original form when the sampling signal frequency Fs having the greater than the frequency value are equal to the input frequency Fm. Here we used two terms Fs and Fm. Fs is nothing but sampling frequency. Fm is nothing but it's an input signal frequency. Here its most important condition is Fs is greater than or equal to 2Fm. It's a sampling theorem condition. Here, in sampling theorem, we have three conditions. First one, Fs is greater than or equal to 2Fm. Next one, Fs equal to 2Fm. Then third one, Fs less than 2Fm. So Fs greater than or equal to 2Fm, it's a sampling theorem standard condition. Then Fs equal to 2Fm is Nyquist state. Then Fs less than 2Fm is called aliasing. Okay. So next, the sampling theorem can be defined as the conversion of an analog signal into a discrete form of by taking the sampling frequency as twice input analog signal frequency. Already told, input signal frequency denoted by Fm and sampling signal frequency denoted by Fs. The output sampled signal is represented by the samples. These samples are maintained with a gap. These gaps are termed as sample period or sampling interval, Ts. Ts represents sampling interval, and the reciprocal of Ts is known as sampling frequency. The number of sample is represented in the sampled signal is indicated by the sampling rate. Sampling frequency Fs is equal to 1 divided by Ts. Ts is sampling interval. Fs is sampling frequency. Then second condition in sampling theorem, Fs is equal to 2Fm. Fs is equal to 2Fm is called Nyquist rate. If the sampling frequency Fs equals twice the input signal frequency Fm, then such a condition is called Nyquist criteria or Nyquist rate. When sampling frequency equals twice the input signal frequency is known as Nyquist rate. It's the most important equation. Fs is equal to 2F. The next one, aliasing. Aliasing is nothing but it's the third condition of sampling theorem. If the sampling frequency Fs is less than the input signal frequency is called aliasing effect. Fs is less than 2Fr. Then sampling theorem statement. Continuous time signal can be represented in its samples and can be recovered back when sampling frequency Fs is greater than or equal to the twice the highest frequency component of message signal. Fs greater than or equal to Fm. It's the sampling theorem condition. So here we can prove the sampling theorem. So we have three conditions. First one, Fs greater than or equal to 2Fm, Fs equal to 2Fm, Fs less than 2Fm. So in next slide, we have to describe or we have to compare the three conditions. So here we used x of t. X of t, it's a continuous time signal. The spectrum of x of t is a band limited of Fm in hertz. Okay, here we used Fm in frequency domain, x of t in time domain. Sampling of input signal x of t can be obtained by multiplying x of t with an impulse train del of t of period Ts, sampling rate. The output of multiplier is a discrete signal called sampled signal, which is represented with y of t in the following diagrams. Here, x of t is the input signal. It's a continuous time signal. Then next, second one, del of t. Del of t, it's a pulse train, impulse signal. Here we used multiplier. This multiplier multiply the two input signal, which are x of t and del of t. This multiplier multiplies the x of t input signal as well as impulse signal. It will produce y of t. Y of t is nothing but it's a discrete time signal. Here, this y of t, the output of the sampled signal. This is the discrete time signal. This mentioned in time domain. Here we used another two diagrams. These diagrams are in frequency domain. Here, x of omega. This x of omega is nothing but we used x of t. This x of t is mentioned in time domain. This x of omega is mentioned in frequency domain. Next, here we used y of omega. Y of omega is nothing but It's a output of it's the another representation of y of t. So y of t is mentioned in time domain. Y of omega is mentioned in frequency domain. Here, represented with y of t, here you can observe the sampled signal takes the period of impulse. The process of sampling can be explained. To reconstruct the x of t, you must recover the input signal spectrum x of omega from the sampled signal spectrum y of omega. Here, x of omega is input signal, then y of omega is output sampled signal, which is possible when there is no overlapping between the cycles of y of omega. Here we used sampling theorem condition Fs is greater than or equal to 2F. So here there is no overlapping between the cycles of y of omega. Next, possibility of sampled signal frequency spectrum with a different condition is given by following diagrams. Here, already we told, we used three conditions. Fs greater than 2Fm, Fs equal to 2Fm, Fs less than 2Fm. So, Fs greater than 2Fm, it's a sampling theorem condition. Here, y of omega, the first diagram, y of omega, this y of omega is represented the output of sampled signal in frequency domain. Here, the analog signals, small gap between multiple analog signals. This is called sampling theorem. This is called oversampling. Fs greater than 2Fm. Next condition, Fs equal to 2Fm. It's a no gap between multiple analog signals. It's a perfect sampling. So this condition is Fs is equal to 2Fm. The next one, Fs less than 2Fm. Here overlapping is there. So this is called undersampling. This is the third condition of sampling theorem. Here we used to y of omega. Y of omega is output of the sampled signal. Next one, aliasing effect. Aliasing effect is nothing but the overlapped region in case of undersampling represent aliasing effect, which can be removed by, we can change the condition Fs greater than 2Fm. So when we are changing the condition Fs less than 2Fm to Fs greater than 2Fm, then you can use anti-aliasing filter. Here we used three types of sampling techniques. First one, analog impulse sampling. Second one, natural sampling. Third one, flat top sampling. First one, impulse sampling. Impulse sampling can be performed by multiplying the input signal x of t with the impulse train of period t. Here, the amplitude of impulse changes with respect to amplitude of input signal x of t. The output of sampler is given by. Here, the first diagram is x of t is input signal in analog form. The second diagram, it's a impulse signal del of t. The second impulse signal is nothing but del of t. Here, these two signals is applied to one multiplier and you will get the sampled output signal. It's nothing but y of t. It's the y of t. The next one, natural sampling. Natural sampling is similar to impulse sampling, except the impulse train is replaced by pulse train of period t. You multiply the input signal x of t with the pulse train and you will get y of t. Here, the same diagram, same input signal, we used x of t. The x of t is nothing but the same input signal in continuous waveform. Next, del of t. Del of t is nothing but it's a pulse train waveform. In previous slide, we use one impulse signal. Then in natural sampling, we are changing only the del of t. So in previous slide, we used del of t. The next slide, del of t is changed from impulse signal to pulse train. Then these two both the signals are applied to the multiplier. In multiplier it produces the output signal y of t in the form of sampled signal. It's in the sampled signal y of t is nothing but the output of the sampled signal amplitude will change according to the message signal. The amplitude of the signal is pulse train in the period of t. Next one, flat top sampling. During the transmission, a noise is introduced at the top of the transmission pulse, which can be easily removed if the pulse is in the form of flat top. Here, the top of the samples are flat, so the noise cannot easily affect the original signal. That's why we used pulse signal. That is, they have constant amplitude value. Hence, it is called as flat top sampling or practical sampling. Flat top sampling makes use of sampling and hold circuit. Here, we used the same input signal x of t. The same x of signal x of t is applied with the same flat top sampling. These two signals are applied to the multiplier and it will produce the sampled output signal. Here we used flat top sampling. Here we used flat pulse. These in previous slide, the first impulse sampling used impulse signal. The second one natural sampling used pulse train. Then third one flat top sampling used constant amplitude pulse. These two signals are multiplied and it will produce the sampled output signal y of t. This the y of t is flat top sampling. It's a constant amplitude in every pulse. So the noise will not be able to occur in every pulse. So easily we can filter the y of t. Okay, thank you.